Okay. All right. Thank you, Wolfgang, for the introduction. All right. So Wolfgang gave a nice introduction. I have to tell you why high dimension, why approximation. Well, first of all, high dimension. If you look at the problems, you know, the world is encountering these days and try to formulate them as a scientific problem, and I list some here. So anyway, here's a short list you can look at of kind of problems that we're facing in the world, and we would like to have better scientific methods to resolve what is going on. And the point I want to make is that, here's a schematic of this, is that one characteristic of these problems is they typically depend on many variables or many parameters. Think of the atmosphere and all the debate these days about the effects of CO2. You could say, well, the atmosphere depends on many variables and how dominant is CO2 among them. So anyway, I would say that numerical analysis and science in general is confronted now with high dimensionality. And a lot of the efforts we're bringing forward are in high dimensions. So what do I mean by high dimensions? Well, I have a function that I'm trying to understand, either simplify, approximate in some way, or maybe I have data and I want to find this function from data, or maybe I can query, ask questions to find a function. But I have some function here, f, and I'll put this in the beginning in the general context that it's a function is defined on a d-dimensional Euclidean space. I'll take the compact cube, that's the unit cube in d dimensions. It maps into some Banach space. Well, you may say, why Banach space? You know, I just like it to map into the real numbers. Okay, you can assume it maps into the real numbers, but in many applications like parametric PDEs, these are the parameters, these are the solutions, and those solutions are functions, and so they lie in some Banach space of functions. But you can think of this as R or Rm for most of the talk. Okay, the characteristic of this is going to be that D is large. In fact, in at least one example I'm going to give, D is going to be infinite. So you got a lot of parameters or a lot of variables, and you want to learn this function or approximate this function for the purposes of, let's say, prediction or answering some question. The typical scenario is either we want to approximate f, I'll call f hat the approximation, or a more reasonable problem or amenable to computation would be just to answer some quantity of interest about f. So quantity of interest to me is some linear functional applied to f. Are we all mature enough to know Banach space, linear functionals? That makes sense to everybody? Yeah? Okay. So for example, you may want to compute some integral of f. This happens when you're doing option trading and stuff like that. You enter into that realm of a problem. You have a high dimensional function and you want to find its average behavior or something like that. Or you may want to find a max or min. You're designing some automobile engine and you're interested in how hot can the engine get, because you don't want it to get too hot, right? And so that may be the only quantity you're trying to minimize or maximize is the max of this function, f. Okay, so these are the two typical tasks. This is full approximation. This is answering some quantity of interest question about f. For example, global temperature. You read every day the global temperature. How the hell do they compute that? Okay, that'll be a question we could ask here. All right, now why approximation theory? Because even though your interest may be to develop a numerical method, this numerical method has to be based somehow on some form of approximation. Typical things you might be not only interested in but know about would be piecewise polynomial approximation, such as finite element methods and numerical PDEs, or you may have heard of wavelets or shearlets. Hey, wake up, shearlets for image processing. But anyway, you have the idea that you're going to take this function and you're going to give a simpler representation of this function. And the simpler representation is to take some space of low dimension, hopefully, and represent f in a space and hopefully accurately. So how accurately can you represent f? That's the questions approximation people ask. Given my target function, we call it a target function f, and I'm interested in approximating it. What tool should I use for approximation? What spaces should I use? Should I use polynomials, piecewise polynomials, Fourier? We have a choice. We'd like to understand what we should do. So given f, and given the method we're going to use to approximate it, I denote that by xn, and you can think of xn as a linear space, like polynomials of some degree, so that the dimension of the space is n. In actuality, we'll be interested in more general ways of approximating than linear spaces. But in any case, whatever method you use is going to depend on somehow n degrees of freedom or n parameters. And when we have the space xn that we've chosen, this is the error we would get in trying to approximate f. So En of f is how well we could approximate f using whatever tool, whatever choice we have made for xn. Okay, everybody seems okay, right? This could be in one variable, this could be polynomials of degree 7. N is 7, or 8 actually, because the dimension of the space is 8. And this would be how well we could approximate our given function in some norm. This guy here, the norm, we can choose whatever is relevant for our problem. If we're trying to do something where we're trying to bound somehow behavior, then appropriately would be x would be an L infinity norm. And if we were doing something where average behavior is okay, or we may choose L1 or L2, least squares problems, for example. Okay. Now the question is, how can we measure how effective the method xn is? Because this is a decision we make, right, in life. We're confronted with some physical problem. Somebody comes into your office and says, I have data here. This data represents some observations of some process, some physical process. Tell me, Professor, you're so smart. Tell me, what should I do to approximate this data? I want the function that's driving this data. How do I get that function? What should I do? Now the burden is on me to come up with this space xn. And how big n will be dependent on how much data you gave me. If you gave me 3 data points, I'm not going to take n as 100. That makes no sense, right? You have the feeling, I mean, if you only have 3 pieces of information, you don't use a space of dimension 100. But should you even use 3? Because that may be an overkill. May not be appropriate. Okay, but back to the approximation problem. So we somehow have decided on some approximation method xn, and we want to say, how well does it perform? How good is it? Wolfgang has his approximation method. Bobby has his. Peter has his. I have mine. Who's the best? Well, mine's the best, but I got to prove it to them, right? So we're going to compare different approximation methods. Now, if we're going to compare different approximation methods, how are we going to do that? And I claim, first of all, we don't compare them on one function. Why? Because in applications, whereas your data problem may involve just one function, usually you don't know what the function is. So you better put in some safeguards that your method can do well at approximating a whole bunch of functions, right? Because you know for sure if you build it based on one function, the devil's going to give you a different function, right, to approximate. So how do we measure the performance of an approximation method? And here comes the idea of a model class. This set K, that we take the view that all we know about F are some properties of F, like it's twice differentiable, or it solves some PDE, or it came from data from the atmosphere, whatever the information we have about F is. And that's the information we have. And we look at this set K would be all functions that have this property. This is a model class. It's what you know about F, right? Well, a model class for us is just a compact set. Of course, which compact set will be important. If I know which compact set, that's an advantage. If I don't know which compact set, but I know it's from a family of compact sets, I can still do something. But if it's a general compact set, well, we'll see. Okay, so one way we measure the performance of our choice here is to see how well it performs on this compact set K. Let's suppose we're in a situation where we know that our function, our target function, lies in some given compact set K. That would be the case if we're solving a PDE, for example. A regularity theorem for a PDE would tell me that the function f that I'm trying to approximate has certain differentiability properties because it solves the PDE. So that's one way, is to say, okay, let's see how well it performs on this class. And when we look at how well it performs on this class, we look at the worst performance. Notice this. It's the soup over all the functions in this class, and we say, well, does this go to 0? How fast does this go to 0? Now, if my method, my xn's, give these numbers which tend to 0 faster than Bobby's method, which is almost surely going to be the case, then I have a better method, right? Because for the purposes of what we know in the problem, I have a more accurate method. Now, of course, it could happen that for some functions in the class, his method performs better, but I'm looking at overall performance, worst case performance. It's called worst case in our lingo. Another way to compare two different approximation methods. So by the way, in this process, I'm thinking of that I have a family of spaces, x1, x2, like polynomials of degree 1, degree 2, degree 3. Why should n vary? Because if I want higher and higher accuracy, I have to take bigger and bigger spaces, right? So I'm interested in what's happening as I crank up n, the complexity of the space I'm using to do the approximation. Okay, another way you could measure whether my method is better than Peter's method is we could look at the approximation class for the method. The approximation class says, okay, let's look at it this way. You have this method. Let's look at all the functions which have a prescribed decay rate. Well, this is not written correctly. Sorry. Okay, AR is, so I was doing slides late at night, so here's AR. AR of this approximation method is the set of functions such that E at F, the error by xn, decays like m n to the minus r, polynomial rate decay. So for example, if r was 2, it would say that taking space of dimension n,
Yeah. Just stick n to the r in there.
yeah, should have been n to the r in front of the ENF here, right? They should be finite. So maybe my method performs with accuracy n to the minus 2, but Peter's performs with accuracy n to the minus 0.1, probably. That's probably what it would work out like. Then mine is clearly better, right, Peter? You agree? Okay, so if you, so if you have your approximation method and you look at this set of functions, if the set of functions in my case is a bigger set of functions than his, then I know whenever he gets accuracy n to the minus r, I get it. But I probably get it for functions that he doesn't get. So that's a way to compare performance of a method, is to look at the approximation classes and say how big are they. We'll return to that. Okay, now we're confronted, as I said, with deciding what tool of approximation to use. What should these xn's be? That's what I'm going to address next. What, you know, if somebody came into your office and asked you to do some data fitting, what would you do? What would you use to do the data fitting? Maybe piecewise linear functions, or maybe polynomials. You know, this is the decision we have to make. And what I want to tell you is that the tool here, this xn, this space, we break up into two types of methods. One are called linear, and the other are called nonlinear methods. And there's a big distinction between them. Nonlinear perform a lot better, typically, than linear, and I want to bring that out here. So what is a linear method to us? It means that, so I say, take this example, for example, approximate functions that are continuous on an interval. This isn't high dimensional. We'll get to high dimension soon. But I could take, for xn, polynomials of degree n minus 1, right? That's a space of dimension n. Because you have 1x up to x to the n minus 1 are a basis for that space. You could, on the other hand, take piecewise polynomials on a fixed partition. For example, you could divide your interval 0, 1 into n fixed intervals. Most natural would be to do it equally spaced. So you'd put 1 over n, 2 over n, like that, right? And you approximate the function, let's say, by piecewise linear functions subordinate to this partition. Okay, that's a linear space. This would have dimension roughly n. True dimension would be n plus 1, I guess. Okay? All right. You could take trigonometric polynomials or Fourier expansions, right? You can use wavelets. You can use whatever you want. You generate an n-dimensional space. And this is the tool you're going to use to approximate. When you do this, we call this linear method of approximation. It's linear because you're using a linear space, xn. That's what linear refers to, not how the mapping from f to the approximate behaves. That may not be linear, but you're using a linear space. In contrast, you could have nonlinear methods. Nonlinear method says, well, I'm not going to use a linear space xn to do the approximation. I'm going to use something more complicated, but hopefully for better performance. For example, you could use rational functions of degree n. Rational function is the quotient of a polynomial divided by a polynomial. If you add two of them together, you don't get another rational function of the same degree, so it's not a linear space, right? If I add 1 over x to 1 over x squared, you figure it out, you're going to get a rational function of degree 3. Okay, so that's a nonlinear set. Another example, an analogy with this would be to allow yourself, when you partition here, to partition this not into a fixed, you don't fix these n intervals. You say, oh, pick whatever one looks good for you for the given function f. So the partition could depend on f. It could be, right? You partition the interval into n pieces, n intervals still, and then I use piecewise linear, but the piecewise linear will depend on the partition I pick. Now if you add two such functions together, if they're subordinate to different partitions, you'll get a piecewise linear function, but it'll be of degree typically 2n, or a number of pieces will be 2n because the pieces don't align with one another. That's an example of a nonlinear type of approximation. Another common example would be to pick a collection of functions which you can think of either as a basis, maybe linearly independent, or a frame, or whatever. Frame is just a generalization. You allow some redundancy. Well, more generally, we call it a dictionary when we allow full redundancy. Redundancy means linear combinations of three of these guys. Maybe I can represent a given function as a linear combination of three guys and then another three guys, the same. So I can't say the representation is unique. So we have this dictionary, and this usually has a lot of functions. Capital N here is large. And then we say, whenever we want to approximate, we reach inside here and pick 7 of them in a linear combination of 7 of them, and that's how we approximate. So that's 7-term approximation. For example, you know, you probably all did something Fourier analysis, right? Where you have the Fourier series. When we approximate a function by the Fourier series, we typically take the first n terms, right? First 50 terms. But we could have been more clever and said, well, we won't take the first 50, we'll take any 50. We'll take the first term, the 7th, 32nd, whichever ones do the best job. That would be nonlinear, because the ones we picked would depend on the function f. Different f. So for example, if you're trying to model signals, and you're trying to write a signal down in terms of sines or cosines, you look at what frequency the signal has its most energy. Where it has its most energy, that's most likely the sine function that you will pick, right? So this is a nonlinear method of approximation because we allow the choice of which n functions to pick to depend on our target function f. Now, I want to organize this a little bit. So I say all these methods you can view in the following way, and this will be important not only for me but for Gita when she talks about her neural networks, that the form of approximation you can view the following way. You have your target function f, and then you're going to have two mappings. One is going to look at f and pick some n parameters. In neural networks, you have your matrices, your offsets, right? You pick n parameters. That's one mapping. And then once you have the n parameters, you have a mapping that takes those parameters and maps you into some function, which we think of as living on a manifold of dimension n. For example, in this piecewise linear, the n parameters would be, what are these breakpoints where it changes linear pieces, and what is the value of f at these breakpoints? So the two mappings would be, the first one would be, I'm given f, I write down where these breakpoints are, that's n parameters, and then I write the value of f at those points, that's another n, that's 2n parameters. Now if Peter receives this information, he can construct the piecewise linear, right? He knows where the breakpoints are, he knows the values at the breakpoints, and he writes down the piecewise linear. Selecting the parameters is A, once you have the parameters, how you create the approximation is M. And we call this manifold approximation because the set M of Z, M, when you start applying M to any point in Rn, right, it describes somehow a manifold. So this is, we view as a form of manifold approximation. It's just a way that is convenient because, you know, if you say, if you open the door and say, well, you can choose whatever way you want to approximate, who knows what crazy idea you may have to approximate. This organizes and says, okay, look, let's be reasonable. We'll look at any approximation scheme that looks like this is fine. But if you've got something more crazy than this, I don't know what you're doing. Okay. Okay, what do we do in approximation theory? As I said, we're interested in two questions. One, how well you can approximate with your given method. And the second would be whether your given method is better than other methods. It's always good if you can show that for your problem you have the best method. Then you'll be very happy. So how do we measure the performance? As I've already mentioned this a little bit. When we measure performance, we don't look at one F. We look at a model class. We say, oh, we gather all the information we know about F, and that describes our model class. These are all the properties that our target function has. So it's one member of this class of functions, K. You can think of it like, for example, the set of Lipschitz 1 functions, if you know what those are. That could be your model class. All right, so model class is a compact set in X. And then as I mentioned before, we would look at the performance over this class. Now, if we have our given method that we have chosen to do the approximation, and we want to evaluate our method versus somebody else's method, here are the type of questions we could ask. We could say, if we opened a door that you can use any linear method, that is, pick any linear space of dimension n, do you have the best linear space? So here, in the competition, I'm only looking at linear methods, using linear spaces. I could open it up to, say, nonlinear methods. I could say, I allow you to use any nonlinear method. Is my method better than all the nonlinear methods in the world? If I can prove that for my given model class K, then I can rest assured that I have done the best I can on a given problem. This competition here over nonlinear methods will be done over these manifold, right, methods of approximation. Now, there's something important in approximation theory that tells us a benchmark as to how well the best method performs. Sometimes it's not easy to find the best method, but you can tell how it will decay for your class. Through some other means, you prove some theorem that tells you how well the best method does in the approximation of K. These concepts are called width and entropy, and I'm going to talk about them next because they provide the backbone, the benchmarks on which you can evaluate any approximation method. Before I do that, I want to point out something important. Even though you may find, you may have your, let's say we're in a situation where I really know my model class. These are the functions I want to approximate. I know K. And I go about and I find the width or entropy, and I say, oh, now I know what the best performance I can make. And then I go further and I find a method that does the best performance. This may not be good enough in a numerical scenario. Why? Because what I'm talking about here is you have full information about F to create your approximation. In reality, you may be only given data about F, and you don't get to choose more data. You're just given the data you have. So these concepts are formulated in the context of full information about f. We'll later talk about what do we do when we do not have full information, when we only have data or the ability to query f. Okay. But, all right, so now I want to return to high dimension, because so far everything I've said is just a general setting for approximation theory. Now, what is the problem in high dimension? I want to caution you that there's a severe problem when you're trying to approximate functions of many variables, and it's called the curse of dimensionality. And that's what this next two slides are going to talk about. So let's look at the typical result in approximation theory. It says, okay, you have this model class, and we will tell you for this model class the best rate you can attain in approximating it with n parameters. Let's say linear methods of dimension n or nonlinear methods using n parameters. So for classical model classes, like the usual way we try to classify a function is on a basis of smoothness, right? I mean, if you're teaching calculus, you say, oh, a function has 3 derivatives, it's pretty nice, but if it has 7, well, it's a better function, right? So you sort of say, well, how nice the function is or what the model class is based on how many derivatives does this function have, okay? So if you think about model classes of this type, and now you have functions of d, little d variables, capital D variables, and you say, what is the best method to approximate? If this is your model class, you know you have this function f, it has 27 derivatives, all of order 27, all derivatives, and they're all bounded by 1, let's say, the size of the derivative. How well can I approximate? The answer is, this is how well you can approximate. And that's the number of degrees of freedom or number of parameters, dimension of the spaces you're using, even for nonlinear methods. Raised to the power s, good. The bigger s is, the better off I am. But I have to divide by capital D. This is the number of variables. So if I have a function that's 7 times differentiable, but it's a function of 100 variables, and I want to approximate it, the accuracy, if I take n pieces of information, think of n as the amount of work I have to do to create the approximation. I'm only going to get accuracy n to the minus 7 over 100. This fact that the d here appears down in here in the bottom is called the curse of dimensionality. The more variables you have, you're going to pay for it. Even having smooth functions isn't going to help you because you're going to pay for it in this dividing by capital D. Curse of dimensionality. And usually we don't have control over S. I mean, it's whatever the problem is tells us what S is. We don't get to choose S. We're solving a differential equation as a solution. We have some regularity theorem that says that the function has 3 derivatives. That's it. That's it. S is 3. So we're stuck there. So this is the curse of dimensionality. And I want to forewarn you that it's even worse than I told you. It's worse because there's a constant in front here. And this constant in front, unfortunately, blows up as capital D gets large. We're going to see this effect of this curse in the next slide. So here's a nice example. You may say, oh, I have a lot of variables, but I have a very smooth function, so I'm saved. I have so many derivatives to my function, I'm in good shape. I warn you, this may not be the case. So here's the example. We take on the unit cube in d dimensions, and we take functions that have all derivatives of all orders, all the derivatives you want, and they're all bounded by 1. Okay, so such a function, all derivatives bounded by 1. And now I want to approximate this function to some accuracy. Let's say I say, give me accuracy a half. And I ask how many computations, or how big will that little n be in the approximation scheme? How much work am I going to have to do? And I'm going to tell you that you can prove that in order to get this accuracy, you're going to have to do this much computation, 2 to the d over 2. So if d is 100, if you have a function of 100, 100 variables, you'll need 2 to the 50 operations, machine operations, which is 10 to the 15th, and probably that's already impossible, but if not, increase d ever so slightly. So you're not going to avoid this curse by being lucky and having a very smooth function. That isn't going to do it. Smoothness is not the answer in high dimensions. So what is the answer? What is the remedy? Because you either say, oh, well, if I'm in high dimensions, I heard this guy DeVore, I don't know, but he went on and on, but he said there's some curse, so I forget about it, I can't do it. No. The curse is if all you know about the function is the number of derivatives, if all you know about the function is smoothness, you're cursed. But the function may have some other properties that you never thought about that could alleviate this curse. And in fact, if you stop and think what people are doing in high dimension now, not only in approximation theory, numerical analysis, compressed sensing, neural networks, whatever, to avoid this curse, they're finding other properties that F could have that are realistic, that is in their particular application, they can prove or they guess or they feel that their function has these properties. And then they say, oh, my function is not, smoothness is not the answer, but it has these other properties, and therefore I can approximate it well, even though it's a function of many, many variables. And what some of the ideas or what these other properties are listed here. So here's the typical other properties that you'll see in the literature when you start reading around about high dimensional problems. And if somebody has a theorem that says he can achieve certain accuracy in approximating the function given some data or given something, he is imposing some new condition about F, and here are the typical ones. One is sparsity or compressibility. So he says sparsity means that when you go and represent it, so let's say we're doing Fourier. We're thinking of classes of functions given by Fourier decomposition. And if you have capital D variables, the number of sinusoidal terms and cosine terms is humongous, right? Because you have e to the I n dot x, where n is a vector in Rd. You have a lot of basis functions, right? The Fourier basis is huge in 100 variables. But the condition you say is, yeah, it had all these, all these functions, yeah, but only 7 of them are important. All the other ones are small, all the coefficients of all the other terms. So your sinusoidal or signal behavior, only a few frequencies matter. All the other ones don't matter, right? That's a typical assumption people impose. Now, whether that assumption is valid, whether that's true for the problem you're looking at, it would be helpful if you could prove a theorem that said, yes, this is true. But that's a compressibility or sparsity. Another type of structure is anisotropy. What does anisotropy mean? It says, I have a function of 100 variables, but really only 3 of them are important. I don't know which 3. And maybe I have to change the representation to see the 3 that are important. But only a few variables are important. The other ones are so weak, doesn't matter. This is anisotropy or the fact that the variables are not democratic. They're not all equally important. Some are more important than others. Another is tensor structures. Maybe you've heard about this, that the variables are intertwined in some way that even though it on the surface looks like it depends on 100 variables, really the 100 variables can be combined in some way that the number of parameters is actually much smaller. And this is a big one, superposition, because everybody thinks that this has something to do with what's going on with deep learning and neural nets, that your function, although it's complicated, it's a composition of lower dimensional functions. If you think of the following, I have a function f of, simplest example here. I have a function f of a1 x1, x1 plus ad xd. x1 through xd are the variables. a1 through ad are numbers. So this is just a dot product of the vector a with x. And f is a univariate. Now this is a function of capital D variables, right? But it's not so complicated, right? It's only, you take a dot product, it's called a ridge function, right? These are called ridge functions. They occur in tomography and, when you're doing these CAT scans and all that kind of stuff. So this function, although it's a function of D variables, it's not so complicated. It's actually has a lot of dimension reduction because it's composed there. Well, there's a general theorem that any function of capital D variables can be written as a composition of functions with fewer variables. Now, I don't want to get into the exact description. This was Hilbert's 13th problem. And who was it, Vitushkin, or who solved this problem first? I don't remember, but there are a lot of results on this now. And this fact that any general function of many variables can be reduced in dimension somehow by composition, by taking compositions of functions, is a very powerful idea. Okay, so this idea that all the functions that we're trying to capture in high dimensions actually have a lot of possibly different properties that make them amenable to being able to be captured efficiently. This is dominating the field, and I have to be careful about the time. We'll take a break at some point. And here are some of the ideas that people are throwing out. This idea of manifold learning, Laplacians on graphs, sensitivity analysis, all these jargons that you'll see are based on the idea that the functions I'm trying to capture have some extra properties, some other properties that I can take advantage of in building my approximation method. Okay. All right, so this is high dimension, and I see I'm talking too slowly, but probably at a good pace for you or not at a good pace for you. If I turn up the crank, that'll be bad, right? So I'll see how far I get here. Okay, so this is the viewpoint we're going to take. We have a high dimensional problem. We're not sure what the model class should be. We know that classical model class, not good. Smoothness, not good. Maybe one of these other model classes based on variable reduction, anisotropy, sparsity, something is good. How do we check whether this new idea of saying use this model class, how can we check whether this model class is reasonable in high dimension? Okay? And once we have decided it is reasonable, and we think our function, our target function, is in that model class, how would we construct a good approximation? Or perhaps prove a theorem about given data, how well it performs. So this is how the next couple slides are going to tell you how, given a model class, you can look and say, does it really break the curse of dimensionality? Because somebody comes in and says, oh, I have this idea. Well, assume that F has this and that property. And you look at it and you say, yeah, but I mean, if that's all you know about F, it still doesn't break the curse of dimensionality. Maybe you come up, how do I know that if I say that, for example, I have anisotropy, I've broken the curse of dimensionality, or what types of anisotropy break the curse of dimensionality? So I'm trying to give you a benchmark. So you came up to me and you said, I have this, Ron, I thought about it last night. I woke up in the middle of the night and I say, this is the set K. This is the properties of the target function. And this is why, even though it's a high dimensional function, I'm going to be able to capture it. And I look and I say, okay, you think this is the model class, right, K? I'm going to check to see whether it really breaks the curse of dimensionality. And how we check it, the first check I want to give is called the entropy of the class. So remember, K is a compact set in X. And I'm going to check the entropy of this class, which means the following. I think it's easier said on a pictorial. This is the K. Think of K as the set in your Banach space X, where you're measuring performance. And you're given an accuracy epsilon that you're trying to attain. And you say, okay, how many balls of radius epsilon will I need to cover all of K? Because if you're going to come up with a numerical method, here's the intuition behind this. You say, I'm going to come up with a numerical method that's going to resolve any F in this red region to accuracy epsilon. Well, then this F and this F are going to have different approximants. And think of the approximants as these green dots, right? So the question is, how many green dots am I going to need to scattered around to resolve this set K? The number of these that are needed, that is the minimal covering, is called the covering number for that given epsilon. Whoops. How many balls? N epsilon. How many balls do I need to cover K? I put in some other topology. Y should be X, I think. There. And then the logarithm of that is called the entropy. It's the analog of the Joe Johnson's physical entropy, right? The entropy in physical systems. This was Kolmogor's deterministic analog of the usual entropy in learning and physics and statistics and other areas. Okay, so now what's the point? If this covering number is huge, right? Suppose this covering number is huge, you're never going to be able to, if your model class requires so many, you want to remember that example of Novak and Wozniakowski to capture to accuracy a half, I needed so much computation. It's because if I looked at that class of functions they had, there were a zillion functions separated here by a distance a half, so that any method would have to, compute so many different functions and made it impossible. You weren't breaking the curse of dimensionality. So entropy. So I just ended here that entropy is a way to check whether you can break the curse of dimensionality. And you may be able to compute the entropy for the class even though you don't know what the best method is to approximate. These aren't the same thing, but you could compute the entropy, and if you find the entropy is small, you shake the guy's hand the next day and say, congratulations, you do have a class that breaks the curse of dimensionality. But if the entropy is big, you say, oh, sorry, you're in a bad situation. You have too much going on. You'll never be able to resolve the functions in this set by a numerical scheme. Okay, there are two other things, and then I'll take a break. Two other concepts to measure how well you're performing and whether this is a reasonable model class in high dimensions. One is the Kolmogorov width. So you may think Kolmogorov dominates this area. He was a very smart guy, but no, he didn't dominate the area. But for concepts about the best performance, he was very instrumental. So what is the N width? So I say you have this class, this is your model class, K, and you're saying that you're going to use linear methods, so linear spaces of dimension n, so that's important. And I say, okay, I have this class K, and I see how well I can approximate K using spaces of dimension n. And I do the best I can. God tells me what space Y I should choose. I have no idea, but somehow divine intervention says this is the best space to use. And then I look at the error this best space gives. That's dnk. That's the Kolmogorov n width. It's the performance of the best n-dimensional linear space in approximating the elements in K. If this isn't going to zero very fast, you can say, forget K, forget linear methods. It's not going to work. I mean, you know, if this goes like 1 over log n or something, you may say, well, then forget it. I can't get any accuracy without a humongous amount of computation. There's a corresponding idea of nonlinear width. And I want to tell you what that is. So remember I said when we do nonlinear, we're going to restrict ourselves to nonlinear methods which are given by these two mappings, A and then M. This idea of mapping, finding parameters, and then once you find the parameters, you find the approximation. So you look at all such mappings, M and A. So you say, oh, I'm allowing you to extract parameters in whatever way you want, and then once given the parameters, mapping into the space X in whatever way you want. It's just that it may be helpful to draw a picture here. So, if this is my set K, okay, and if I were doing linear widths, I would say I can use a linear space to approximate K. So that means a linear space would be like a hyperplane, actually, right? Slicing through K, and you try to choose this space so that the distance of any element to the closest element in this space is small. And the Kolmogorov n width is saying, well, what would be the best way to slice through this space? Now, when you do nonlinear width, you say, oh, you don't have to slice through with a linear. You can slice through with somehow a manifold, right? Okay? But if you think from the point of view of reasonableness, is it reasonable? You should be a little bit leery because you once learned as an undergraduate probably that you can take a very complicated set and find a space-filling manifold, right, of one dimension, a curve of one dimension that every point is close to this curve, right? A point on the curve. So you say, wow, then with n equal 1, I can approximate anything. Well, the problem is that these two mappings, A and the recovery, are very, very bad mappings. So what we put some conditions here on the mappings in order to say that this procedure is reasonable. And there are two types of conditions you can put. One is continuity. You say that A and M are continuous. That was the original definition done here at South Carolina. This Ralph Howard. Charlie Michelli isn't from South Carolina, but he visited. The other is that we have realized recently that this is too weak. to assume just this. From a numerical point of view, it's too weak. See, what would be bad numerically is if, when you extract the parameters, if you extract them and they're close, but yet the approximations after you apply m are very far apart, that would be bad. Another thing is if two functions are close and their parameters are very different, that would be bad. The lack of numerical stability. So here we modify this definition by requiring that these two maps are Lipschitz maps. And that way we get what we call stable widths. And it's going to turn out that this is going to be an important issue in the next hour. Okay, so now we should take a break. Is that okay?
Sure.
Am I doing all right?